Good afternoon. So welcome to this Bose Colloquium lecture today, and we are very happy to have Professor Tarun, who is the director of Raman Research Institute, with us to deliver this talk. To begin with, I request our Dean Academic, Professor Amitabh Lahiri, to present a flower bouquet to the speaker. Thank you. I now request our director, Professor Tarun Gupta, to kindly introduce the speaker.
Very good afternoon, everyone, and thanks for coming for this Bose Colloquium. Today's Bose Colloquium speaker is Professor Tarun. Many in this hall, I'm absolutely sure, are quite acquainted with all the contributions of Tarun, but as a custom, I need to introduce him. So, as has been already mentioned, Professor Tarun is currently the director of Raman Research Institute. I was going through his profile, and I actually didn't know he started his career as a mechanical engineer at IIT Kanpur. So I now know of another engineer who switched from engineering to physics. And after that, he did his PhD and also had a long career in IUCA. So after PhD, he had two postdoctoral stays, one in Kansas State University and another in Canadian Institute for Theoretical Astrophysics. He is a very accomplished cosmologist and also a brain behind, all we are seeing today about the LIGO India project. He was the former spokesperson of the LIGO India, as well as one of the main detailed project report writer. And, basically driving a mega project is actually a very difficult job. So I think it is a proud moment for all of us, because finally LIGO India has been announced, and our India is a proud owner of this project. And I first met Tarun actually during the long time back when we both went to Delhi for this Souradeep meeting. And I was pretty impressed by his name. Person having a name, Tarun Souradeep, that already gives a message to the society. And I had little, information that he is actually a Bengali. So started talking to me in Bengali, and I was very surprised. The person with the name Tarun Souradeep, how can he get that? But then I understood, and then I felt that it also is said. So with that, I invite Tarun for give the talk on standard cosmological model. And I can see in this hall many young faces. They are basically, I think they all came for the CKM workshop. Who are the students? They are from either master's first year or bachelor final year. So I do hope you will get further motivation to carry out your future path with this fascinating. So,
So let me begin by thanking Tanushree for the invitation to the Bose Colloquium and the nice colloquium, and for the very generous introduction. So to Amitabh for the nice bouquet of flowers. This is the first time I would have got a bouquet of flowers from you. I don't expect a day like this, but that's nice. So let me get to the talk. I'm going to give you sort of glimpse that where the frontier of cosmology is this time. Of course, cosmology is a vast subject, so I will be leaning on one particular aspect of it, but it's the global aspect of what we understand about the universe and its origins and history. And it's important to realize that it may not be such a surprise for the young people here, but when I started cosmology in 1990, there was no real accepted cosmological model. And now it amuses me that a lot of cases people mention standard cosmological model without these quotes. I insist on putting them because it should not be confused with the standard model of particle physics. There are differences, and I try to mention them, or you can ask me later. Nevertheless, over the 3 decades, the progress has been, enormous and spectacular, and I will give you a glimpse of that. And largely, I'll focus on the results from the Planck satellite, which is the latest in series of extremely capable observations of the cosmos that we have done. Planck was with the European Space Agency, and we were part of this from India, the only group from India part of it. And so let me, however, first begin by introducing to Bose. It's a real great honor to be called for a Bose Colloquium, and I really thankful for that. And I thought it's really befitting that I'll be talking about bosons, and it's a tale of bosons which really mediates our understanding of the early universe and our current universe, right? So it connects. And also, these days you need to give a lot more in favor, arguments in favor. So arguably, these are the most informative bosons that we have. It really tell you on the cosmological scales what's happening, and they are also very numerous. So every cubic centimeter anywhere in the universe has about 400 of them, and they determine the entire dynamics of the cosmos. When the cosmos was young, right? So in its first 50,000 years, largely it's the same micro background, micro background, determined everything. And I had a different photograph, much photograph I saw most, but today I was also lucky to visit the archive, and I saw this, which also had a very apt tagline, the man who counted photons, right? And so we are talking about looking at photons, the most numerous or most prevalent photons in the universe. So okay, so this is a movie. So this is a fly-through, and she did mention they're young students. So this is how much we know about the universe. This is, of course, a simulation, but you see, if you fly by into the universe on some fancy Mark space thing, you will see this clusters of galaxies, and you see that matter is kind of numerous matter is all there in these galaxies. And if you look at the distribution, it's a very organized but large-scale structure, right? So you can see that. Of course, we will deal with a lot more about the details of the galaxies or the clusters. I'll be talking about the big picture of the universe being full of galaxies, and these galaxies are not really put in lattices or very regular things. It's in a very organized structure. Many of you condensed matter see such things all the time. And hence, the important part is we can describe the universe and its matter distribution largely statistically. So it's kind of a random distribution with certain patterns in it, and we want to understand where, what can be done about the universe. As physicists, you always, if you are, given a huge universe with galaxies full of galaxies organized in substructure, looks like a very complex problem. But as physicists, you look for simplicity, and this was realized long back observationally, that if you did project the galaxies back on the sky, there was no particular direction in the sky which really cried out for attention. Of course, you see this clumpiness there, but the clumpiness is more or less the same. This is a picture from the 1970s. So even then, people knew it's a reasonable guess, first guess, that the distribution of matter around you is isotropic. It's the same in any direction. There's no particular direction. If I looked out in this direction versus that, and then you take a leap of faith, which we do. We don't want to be like, since Galileo, we learned that we shouldn't think of us being in special location like our galaxy. So if you believe that we are seeing an isotropic distribution of matter, and this would be true for any cosmic observer in any distant galaxy. Now, just a simple theorem of mathematics tells you that isotropy around every point means that the medium is homogeneous. And of course, all this was not talked about when Einstein first put the cosmological models in them, because of simplicity. But these are probably the simplest problems to solve in general relativity, right? What can be simpler? The right-hand side, which describes matter distribution, is just homogeneous and isotropic. But yet, even in that simple thing, we were led to surprises. So much so that even Einstein balked at it. He found that the universe was not static; it was, expanding or contracting. He was very worried about it. He found something called a cosmological constant. It's static. It was displaced, but all kinds of things like that. So this is the smooth expanding universe. So what I want to tell you is all of cosmology is built upon this very simple idea that we are in no special place and there is no special direction. This is fancy name for that is the cosmological principle, or in modern language, it's that statistically we have an isotropic and homogeneous distribution of matter. Okay. If you give me that universe, then over the many decades since 1952 or so, people could work out using very basic physics in the lab, what must have happened in this expanding universe in the past. So this is us here with this galaxy distribution. And in different wavebands, we peel off different layers, and you can see there is things forming here. The end of dark ages, and this is where James Webb telescope is looking at. And then we have this screen here, which I'll get to. And before that, it was a very dense universe with every kind of physics that we can imagine, any energy scale, must have played out in the history of the universe. This is our big. Okay. And the biggest support for this comes from something called the cosmic microgravity. I said these are the most abundant photons in the universe. If you ask how much of the energy density of the universe, where in radiation, where is it? It's in this cosmic microgravity. So when you look out to the sky, we're also lucky that in this waveband between 60 to 600 gigahertz, you can peer back 43 billion light years and see photons coming to us from a time when the universe was 500,000 years old. Remember the current age of the universe, which is known more precisely than this rough number, it's 30.7 billion years. Right? So you see how much of a time scale these photons are bridging. Okay, so the picture you should have as an observer is we are able to look out in this band, the furthest reaches of the universe. So this 14 gigaparsec translates to 43 billion light years. Giga is 10^9 and a parsec is about 3. Okay, and then you hit a plasma screen. So how much luckier can you get? We have a Cosmos has presented you with the IMAX theater. It says a plasma screen, 43 billion light years away. Okay, and from 1965, when we first discovered this, till 1994, we couldn't detect anything on it. Of course, it was probably getting a bit boring because you don't want to sit in IMAX theater and see a glowing screen, but nothing else. But then we got smarter, and in 1992, the first pictures of tiny variations at 10 to the power of -5, 10 parts per million, started showing up on the screen. Okay, and that, remember, are fluctuations on this plasma. So these were density waves, and velocities of the plasma that were reflected in temperature fluctuations that you see in this. Okay? So it's a amazing laboratory that you have where you can see the early universe at a very early time. You can see things happening, and these are all based on physics, which is very well known. Okay, there's no fancy physics here at all. Okay, this is all resonant phenomena and plasma, things like that. So it's only thing is the stage is very fancy. It's this cosmos itself, and the stage is also expanded. So that's the only thing you have to wrap your head around. But otherwise, it's fairly straightforward physics. And I said it's amazing that the universe is largely transparent up to this wall in this wavelength. So what does it tell us? So this fact that you see this glowing plasma and that the plasma, you look at its energy spectrum, follows what is called a black body curve. It's a special case of Bose-Einstein statistics. Okay? And the fact that it's a black body curve, not any Bose-Einstein distribution with some chemical potential, tells you that the universe must have been 10 million times hotter than what we see now. I forgot to mention the temperature of these photons, of this black body that we see now, we measure it to be about 3 Kelvin. So this plasma screen actually is the glowing plasma screen at 3,300 Kelvin. The expansion of the universe causes that those photons redshift and produce a 3 Kelvin environment. And the fact that we have a perfect black body tells you that it must have had a universe where photon non-conserving processes had contributed to setting up that thermal equilibrium. Okay, so one simple observation tells you that the universe was hot in the past, fairly hot. Okay, and then people extrapolate it further, because if you do that, then you can explain the abundance of light elements. So, and then we saw this fluctuation and we were delighted, because I showed you in the first video itself that the distribution of galaxies is not very smooth. You can see a lot of clumpiness in that. And where did it all arise? So we knew that if the matter distribution is clumpy, the radiation must show some clumpiness. And this is why, in 1992, when it was discovered, it was heralded a lot, because it was the first time we saw hints that there were indeed tiny perturbations in the early universe, which could then grow due to gravitational instability and give you. But of course, the question is, you have the plasma screen, you have fluctuations, and you know how to connect this to this science, physics. The question is, what caused this fluctuation in the first place? And that's still an unresolved problem. So if you think cosmology is all done, you're wrong. This is the next horizon, right? Next frontier. Where did these fluctuations arise? Our best guess, and not surprising in this era of quantum technology and application we talk about, this was the first time quantum physics played a role, and these are actually quantum fluctuations in the early universe, which gave rise to these density waves as well as gravitational waves. Okay. And I'll come back. So now you have this screen around you. Astronomers take the entire sphere and project it on these oval-shaped projections, equal area. So this is the temperature fluctuation shown at low resolution, angular resolution. Just to reveal that there is also additional information in linear polarization. Not only is the temperature little higher and lower at different directions in the sky, but also if you take a polarizer sheet, you will find that the intensity is maximum at a particular angle. And you draw a stick. So you have a field of sticks. You have a temperature fluctuation. Temperature fluctuation is the scalar field on a sphere. If you have a field of sticks on a sphere, headless vectors, you can do what we do in physics very well. You can express it as a gradient of a scalar and a curve kind of operating 2D sphere of a pseudoscalar. Okay? And these are two polarization modes that we can in principle measure. So there's a lot of information in the micro background sky, and we have uncovered quite a bit of it, but not everything. Okay? And there are, various statistical quantities you can form. If there's no parity violating physics, then there are 4 measurable quantities. If there is parity violation, and then there could be other 2 which will show up. And that would be amazing because it will completely reveal that there is something. If you see something like in these, it tells you that there has to be some parity violating physics. Okay. And as I said, I won't take too long on this. I mean, I just wanted to emphasize here that the physics is very well. Okay. It's very simple resonant physics. You can see that what you see on the sky is actually sourced by resonant fluctuations. So if you take the Fourier transform of that, you will see that there are series of periodic peaks, right? And that is what happens when you play music. In a flute or on a resonant tube experiment, you're setting up standing waves. So these fluctuations that you're seeing are standing waves in the plasma due to whatever fluctuate, cause those fluctuations. And in the green function picture or in the real space, what you can imagine is the whole CMB fluctuations that you see are made up of these spikes with a ring at 150 megaparsec. Imagine this, it's a decomposition you can do. You can do Fourier decomposition, you can do this decomposition. And this is interesting because you can go back and imagine a lake. I just saw the Salt City Lake this morning. So it looks very placid. Imagine a burst of shower, right? And you take a picture 10 seconds later. Of course, you see choppy waters. And you would think, oh, there's no information. That's not true. If the shower was, at one point of time, very sharp in time, then everywhere a drop fell, a ripple started, and when you took the picture 10 seconds later, the ripple would have traveled some distance. You can calculate that. You take a Fourier transform of that picture, and you can also look at the velocity. This is what we are doing in CMB. We have the plasma, which has these fluctuations. We're doing a Fourier transform and seeing a series of peaks, which are essentially the Fourier transform of this ring, right? And the ring is at a particular scale because, just like I took a picture 10 seconds later, at 20 seconds, the ring would be double this. So this 150 megaparsec is a scale that is imprinted on a screen that is 43 billion light years away. So you can read off a lot from there, okay, of the physics. The strength of the ring gives you the amount of baronic matter is there. The angular size obtended gives you the geometry of the universe. And that's why we are able to know a lot, because we have been able to measure all these things extremely well from this microwave background skies. The acoustic horizon, the distance sound travels in that plasma, in the age of the universe there. And then, we also have seen the similar ripples, the distribution of galaxies, which is another story I will get to. But main point is that the CMB physics is very well understood. And that's why we trust what we get, because you know what you're talking about when you're connecting it to observations. So there have been 3 decades of observations with milestone missions. One was the Cosmic Background Explorer, which first gave you that black body curve as well as the first fluctuations, but they were at low angular resolution. Then there was Wilkinson Microwave Isotope Probe, which improved the resolution, gave us a lot more information to get. Now, the last decade was the Planck results, which final results came out in 2018. And then there's the question of what happens next. And there have been a lot of ground-based observations. And this is really an amazing field. I wanted to point this out because I told you in 1992, that's around the time I started my PhD, and some of my friends here started it at the same time. This shows you the amount of information we have garnered about our cosmological model. When I told you we hardly had a cosmological model here, very clear model, we are here. Now, whichever curve you do, we are at least 1 billion to 1 trillion times more information. And this is in something called a figure of merit. It tells you what's the volume of the uncertainty space. And this growth has been 3 times the most long. with this thing, a remarkably successful field, and it's really revealed everything that you wanted to know about the universe very efficiently over time. And this is Planck. You can see that we are still going ahead with much more sensitive instruments going forward. And these are all, currently under deployment. So this is the Planck all-sky map. So this is what we are seeing on the IMAX theater screen, the full sky. And you can see that now we have enough information to even, remove what could be our contamination from the galaxy and all that. And you can see a full sky map. This is shitty. Not only that, I told you about that polarization field. So those, instead of string of vectors, it shows you like a beam line. And we have been making very impressive maps of also the polarization on this polarization field on this sphere. Right? The question is, what will it get us? So if you go to the Fourier space, it got you one of the best measured power spectra. So you can, these are actual data points with error bars. So to see the error bars, you have to subtract that best fit line. You can see indeed there are error bars. But it's a very impressive measurement that we have of what's happening to the plasma intensity. Similarly, they have something similar for the polarization field. I won't get into all. I told you of these, different power spectra that you can get with polarization. But this, you can see these are fairly well measured, but not really as well measured as we want. And then we have been able to detect something very subtle. The fact that the photons are coming to us, and there's a large scale distribution, there's an inhomogeneous distribution of matter along the line of sight. It creates a signature of weak lensing. So the photons are not really traveling along the original path, they get deflected. And that deflection is very subtle, but we have been able to detect it very remarkably, and just to show that around hotspots, you see a convergence of these, and around empty spaces, you see a divergence as you respect from gravity. And you can make a map of the integrated mass in the universe. And this is the signal to noise is as of the Kobe map when it was in the 90s. So you can see that this field is going to grow remarkably in the next decade or two. And you will have maps with exquisite signal to noise on the distribution of matter along the line. Okay. So the game in cosmology then is very simple. I told you we have a very simple cosmological model. Isotropic and homogeneous model. You put whatever matter into it, it's a very simple equation. Then you can compute everything well because there's really very little doubt on the physics that's happening. It's very simple. So I can take, you give me this homogeneous model, you give me your recipe of what the universe is in terms of how much of baryonic matter, how much of cold dark matter, how much of dark energy. These are names probably you all have heard. So give me everything. I can calculate very robustly what the predicted CMB power spectrum should be. And I showed you how well we have measured this. And these are the green dots. So now it's a fairly like a game that you might want to do. Multiple dials, you keep dialing them, and then look for a combination where this thing fits. So you look for a combination of parameters where the black line threads all the data points. You can see if you have very well measured lines, not every combination of this, a very limited play to the combination that will work. And there's very little play. So hence, that's why we know the cosmological parameters exist. So for the first time, we know the baryonic amount of normal matter in the universe to a person. And these are getting to other fields where you do precision measurements. We know how much of cold dark matter is there to about 2%. Okay, I told you about this, ring size of the ring. That we know to exquisite accuracy, about 0.04%. Okay, that was 0. And then various things like how fast is the universe playing. So these are things that it was difficult to even imagine it would happen within a research career. Because this was known to a factor of 2 when I started my research. Okay. And this is just to show you how rapidly over the CMB, CMB observation, these things are very rapidly, all these parameters are gotten very well defined. And so we have a simple model that works. It explains everything that we measured till now. And then that is what is being called the standard perspective. Now, why wouldn't I just declare victory and say, let's cosmologists start doing something else? That's because 95% of the energy of the universe is some exotic form which we don't know. Okay? Part of it is dark but clusters under gravity or dark matter. Another part is dark in the sense it doesn't have electromagnetic interaction, but it's a smoother form of energy that doesn't cluster under gravity. Okay, we don't know specifically what they are, but we know they must exist under the model that we are working. And the other part is that, remember, I told you that we are building the story by connecting the fluctuations we are seeing on these plasma screens to the universe we have seen now. But what gave rise to that? That must be some ultra-high energy physics which we have not uncovered yet. Okay? So that's something that really needs to be figured out. Along the way, that's, so once we knew that we will get the cosmological parameters very well, so part of the community started working on, is the model that we are standing on robust? Is the universe really isotropic and homogeneous? Is the cosmic thermal history really what we think it is? And then, we said this funny thing about, there's a plasma screen and it's oscillating. Is that all right, or is it a fairy tale? Then we need to make up. We said, there's large scale structure happening and the small fluctuations grew to give you the large scale structure. Do we see clear evidence of that apart from the micro background? And what generated the. So in terms of paradigm of dynamic fluctuations, the fact that there's an acoustic phenomena happening. So I give you something bits on that quickly. So one is if you take something like the Planck measurements, the power spectrum, you can say, okay, I don't know anything about cosmology. I give this to someone who is good at curve fitting, and completely agnostically ask, is there anything interesting about this data? So clearly, all of you would see that even from this scatter of points, you can see that there are peaks I can identify, and then you can ask where in this multipole space, which is inverse angular space, are these peaks? How are they lined up? And you can show that if I take the first peak versus the second peak versus the third peak, and plot them in this form, to any physicist, it would immediately remind you of some structure which is regular, like crystallographers and things like that. It immediately leaps at you that the data, even without any idea of what the cosmology is, tells you there is resonant physics happening. And then you can look at the spacings and all that and already guess, is there a specific scale to it? And this is all model independent. I have not used any cosmology in this. And we could see that we could get something like the acoustic horizon scale, not as accurately in the model way that it can get, but fairly clear that there is a scale which is picked out by these array of dots that I'm showing. And that's, as I said, measured to 0.04%. There is now an even clearer signal of this acoustic physics. If you look at the sky map, I told you there's a polarization field and a temperature field. Look at the hotspots of the temperature field. These are density peaks. Okay? And then you stack all the polarization field around all the hotspots. And you see this ripple stand out. Okay, this ripple has the same 150 thing on it. And if you do the cold spots, stack up the cold spots, then you see, if I go between the two, you can see this radial pattern changes into this tangential pattern, and the tangential pattern changes into this. So what I can tell you is the polarization field is sourced by velocity. And if I have a density, positive density field versus a negative density field, it's easy for you to see that the velocity field will change sign. So wherever the velocity field had a maximum, it will minimum, and a minimum. And we see this here. Now, the other question you can ask is, can we really go more carefully whether the universe is indeed the same in every direction? Is there any signs of it? So one of the predictions of that, or prediction of the cosmology principle, is that if I give you a CMB sky map like the one I planned, and I give it to you in rotated coordinates, I don't tell you which direction it was, I should not be able to get any new cosmological information. So that means there is no specific direction to the universe as far as the cosmological background fluctuations go. So in technical terms, it means that if you look at the Fourier transforms of the sky map, they are uncorrelated. Just like on a homogeneous fluctuation, which is fluctuation, the wave vectors are uncorrelated. Here, the angular vectors are uncorrelated. And you only have this angular mass vector. However, if there is information which is, cross correlation between two different modes, they can be captured in the same way that we do in quantum mechanics in a total angular momentum representation. And this is what we developed as a pi-Posh spectra. And this is one example of a universe which is also homogeneous and isotropic locally, but globally as a topologically non-trivial structure, it will give you a lot of information that you can glean from the maps. So what we showed in 2003 is that this is a measurable quantity. I will get you to this part and ask you later. Measurable quantity that can probe whether the universe has some isotropy, some special direction, isotropy breakdown or special direction. And that can happen if the universe is globally a torus, right? It looks flat and infinite, but it need not be. It can roll up on itself, and that will have a direction. Then you can have global anisotropy, rotation. This time we talk in equilateral time where there are all these models you can have where the universe has anisotropy, and these can be all, there can be very stringent limits put on these with the data we have. Then global symmetry breakdowns will show up there. And there are a couple of things we expect to see. One is the fact that our galaxy is moving at a fairly large velocity of 300 kilometers per second with respect to the cosmological background. That can be seen, and the weak field lensing. The other part of it is you always worry when we measure the sky. Are there some observational artifacts which is, kind of hiding there? And there are lots of them which show up in this. So I won't be able to give you examples of that. But the broad thing is, till 2003, we used to only measure this angular power spectrum CL. But now you can measure a whole series of angular power spectra and ask, are they consistent with zero? If they are all consistent with zero statistically, then the universe is homogeneous isotropic. Otherwise, you have a issue. And so how are we doing? So there was one mystery that persisted from the days of Kobe, Cosmic Background Explorer in 1990, is that Cosmic Background Explorer did not see such a high resolution map. So something like this. And some people noticed that if you divide the sky into two along this line, two halves, then the fluctuations in this half are markedly more pronounced than in this half. Now, at that time, it was a curiosity. People said, Kobe has only 3 frequency channels. A lot of things can happen. But it persisted in WMAP, persisted in Planck. So we were invited to the Planck collaboration to measure this. And we did show that it's about close to 3 sigma effect on large angular scales, that you do see that the fluctuations on one side of the hemisphere is 14% higher than on the other hemisphere. But the statistical significance doesn't cross 3. So it's not something that you can call discovery, but it's very intriguing. And it can never cross this unless we have some additional information. But so what we would do is to show that this is unlikely to be anything other than a cosmic thing. Because if you looked at Planck, it was a fairly robust experiment, and you looked at 3 different frequencies, you see the same effect in each of them. It's not something which is probably some foreground contamination or something like that. And we stopped in Planck by giving, as a part of the collaboration, we only used some frequentist measure of a p-value and said that this is intricate and can happen only by chance 6 times out of 1,000, right? And that was our thing. And we could also locate the direction, and that was important because this direction did not really align with any known direction plane. If it had been the ecliptic pole or the CFP dipole, it would have had some hint of where it comes from. At this point, we really don't know what it is. But the question is, how statistically significant is this? Frequentist thing was fine, but we said, why not a fully Bayesian thing? And we extended this our capability to a fully Bayesian analysis of a random field on a sphere, right? So that is more general than just the same fluctuation. And we have that framework in which we looked at the same effect, and we could take into account all the other things, like we don't need to remove some part of the data because of galaxy, galactic contamination, some with the scanning. We basically showed that this thing persists at odds ratio of 0.25. That is not something that we'll feel very upset about, but it's very surprising that it doesn't support the statistically homogeneous model at a, this should have been 10 or 100 if this effect was not there at all, right? So it's kind of says there's something interesting, and we can look on that. And there are possible avenues for looking at that. I won't get into that, but we showed that it will show up in the polarization measurements from what are being carried out in South. And then, so this is the health report. We see it in a very natural statistics, so it's not a designer statistics. We do a Bayesian estimate, and the best available CMB map do not pull out a non-SI map. I mean, it doesn't say that it's not there. Similarly, there was another attack on the isotropy which came recently. So you see, we are moving with respect to this plasma screen. So obviously, the plasma screen will be slightly hotter in the top left and colder on the opposite side. And we have been seeing that as the CFP dipole since the 70s. So it's a hottest spot by about few millikelvins here, and the coldest spot by few millikelvins, right? And that translates to a velocity of 380 kilometers. But then there are questions of, is this really all that dipole that you see? Is it all kinematic? Okay. And in fact, there was, so what you do is you have to look at your motion with respect, we are looking at it with respect to this cosmic screen. Then we can look at it with respect to distant quasars, right? And people did that. And there was a paper which kind of challenged this cosmological principle, saying that what they see is a velocity which is almost double of what is measured by the CMB dipole. And the curious thing to me was, but there is other ways of making sure that the dipole that we see is consistent. Yes. So we had shown in the plan as a test, we had tested our method by actually measuring this dipole anisotropy using the bipolar spherical harmonic thing. But we used it as a calibration. Like if you measure this right, so what is happening here is if you're moving at characteristic speed, the entire sky bunches up in front of you. This is called aberration. So this is something that shows up as a statistical isotopic violation. If you have a direction, you can map, and you can measure it. So I will, there are off-diagonal elements of this which you can measure, and then you can put your entire Bayesian, mechanism to get a number. But you can see that the direction that we inferred from simply kinematic effect, special relativistic aberration effect, matches up with the CMB dipole very well. And we detect this amplitude to be consistent with the CMB dipole at 5 sigma. Now, this you can ask why didn't Planck do it at that level? Because we always took it for granted that nobody will question that. Because always, so we do it what is the best possible with the data available. And we assured ourselves that 5 sigma, this is consistent, and also the value inferred from the quasars is actually, extremely unlikely. Okay, so the this thing is 5 sigma, and I have that number, but it is ruled out at odds ratio of 10 to 11 or something like that doubles the velocity. So either something is going, most likely this estimation from quasars is doing something very different from the estimation that we're doing with the supercosmic background. So this is something that we still have to figure out. So let me quickly talk about how much do we know about the early universe from which these fluctuations first arose. I think that is a big question that cosmology is faced with. So now if you have some early physics, you always think there will be some signs of it somewhere, right? That physics would have some scale, something would happen. So as I just to repeat myself, our success in cosmology has largely been from matching this cosmic screen, 43 billion light years away, on that, with the current universe through galaxy formation. Okay. Now, the question we're asking is who created this fluctuation in the first place? So now, for best guess, there's quantum fluctuations in the early universe. We know the physics, the quantum theory on growth based time is correct. Then we think we know why such density fluctuation created during a period of very rapid expansion called inflation. Okay, but it's a paradigm under which we work. But amazingly enough, everything seems to be checklisted on this. Okay, and the only thing not checklisted. So this is just summary table from the Planck final results, saying that everything is consistent with Gaussian fluctuations and the story that inflation tells you. Okay? And we have measured things like the index, shape of the curve, spectral index of this extremely well at 5 sigma. And I told you that we know that there is acoustic physics happening. And yeah, so if that other thing didn't impress you, this is really good. Right there. Okay. So before I finish, I wanted to just quickly say that there are still openings. You can ask, we are assuming a featureless power law spectrum of fluctuations in the early universe. If there was some interesting physics, wouldn't that imprint some scale on it? So then what you can do is, instead of assuming the model of the initial power spectrum and then use the constant factor bracket to get the parameters and the power spectrum, you can reverse it. Okay, it's a reverse problem of taking the anisotropy data and cosmological parameters and ask, what is the initial power spectrum I get? This is something that we started in 2003, and it's a program that's still going on with data. When we first applied it on WMAP, we saw that there was an evidence for some cutoff and some odd features like this. It's as if, it's like some mastering thing, which is under tap, goes and taps out like this. So if this is true, then it could be signaling something. The question is of evidence and how strong is the evidence. So that large angular scale will revive strongly. But we did that 10 years later with Planck. And then, this is the current thing from Planck, which is showing that, yes, even if there are features, this is very difficult to say that there is anything that stands out against noise. So now we are left with another route. That is to see gravitational waves from the same epoch which created this sense before. And this happens in inflation, and this has to happen. Okay, it's it's a inevitable thing. you believe that the density contributions were generated due to quantum physics in the inflation field, then it must correspondingly have gravitational waves. And these would be gravitational waves from the beginning of the universe. This is a grand ambition. And we see even Ray Weiss or Kip Thorne, when they gave the Nobel lecture or recently the pulsar timing thing, keep repeating that the most exotic thing that we are looking forward to is to see gravitational waves from the Big Bang. And this is seen in the polarization field of the gravitational waves of the CMB sky. So what we need is a near ultimate CMB polarization survey. And besides doing a lot of other things, it will reveal a signature of quantum gravity or quantum filtering across space-time. And can add more things to it. And this is a proposal that we put forward to ISRO in 2018. Ambitious CMB satellite, next satellite. It would be around 4.4 meters in diameter, fairly large satellite, which GSLV Mark III, which launched Chandrayaan, can take. We take it to the second Lagrange point and give you the information that we're looking. And there were a lot of people. This community has grown from the days we and Simon were graduate students, and you can see that a lot of very capable people in the field can take it. I'll stop here and say that cosmology has been extremely successful. Field of cosmomicro background in particular has been a remarkably successful field, but it doesn't mean that cosmology is done. That's very important to emphasize that we are just beginning. We have just basically found a solid ground to stand on and query the universe. And you will never know what the universe is made of. Like what's the present. Thank you. Nice talk.
Yeah, maybe young people should ask, but yeah. So regarding your proposal of this,
to use the microphone for those who are online with us here.
is there a, by the time the mic comes, I maybe change to.
You might forget your
Another
question.
question,
We
yes,
have not
yes.
seen that
Yeah,
out.
maybe. Yeah. So let me ask what comes to my mind now. So this was regarding your proposal of this.
Yeah.
So what exactly do you plan to measure? That wasn't clear to me. Using
So
the
we want to measure the temperature fluctuation have been measured to the angular resolution required for basic cosmology type, what I call primary signal has been measured by Planck. But 90% of the polarization information still is untapped. So although they're very impressive, the measurements look impressive, but if you go by signal to noise, we know that we have 90% of the measurement. So we need something that maps out all the information on this, CMB sky maps or the IMAX data. And that's something that we need to, because that's out there, as I said, it's a unique kind of thing nature has provided, and we need to do it. And in doing so, we may discover something as fantastic as gravitational waves coming right from the beginning. There's a very high chance.
I see. So you'll get signatures of gravitational waves on the polarization.
Yes.
That is what.
You know that it's a shear field.
Yeah.
So there is this.
So you're likely to get. So that is the. So I have other questions also, but maybe I should wait for younger.
Yeah. Let me check with that state. I'm sorry, I was a bit too rapid, Prof, because I didn't expect so many young people like that. So, younger audience. So maybe the experience one speech.
Shine, you want to ask something? Maybe Shine. Yeah. You quoted some eternal value, right?
Yeah.
Is that good? The number that you quoted, 2.3 plus minus.
Yeah. Pretty good.
I mean, is it?
Trustworthy. Talking to a former class.
No. I'm saying that 2.3 plus minus 5.7. What does it mean?
Oh, okay. It means that you don't have an FNL. Right? So
Deviation is more than the middle.
Yeah. It's essentially not perfect.
It's not
There is no longer sense.
I mean, to this accuracy, right? If you take what you sigma thing plus minus 10, we don't know. So you need this sequencing match that I showed you. That will reveal a lot. Then, of course, in the distant future, when we see neutral hydrogen fluctuations, that, as you know, will get you FNLs of the kind that inflation also imprints an FNL, but that's of order 1.
So this is within CMB observation.
Yeah, so the reason you see this 2.5 is because there are diesels for which non-Gaussian tests, which are not primordial, highest order effect, which gives you a non-Gaussian TFC. Those are taken out, and to the extent to which you have taken them out, they can.
And in your last part, what you mentioned was you wanted to see the cosmological gravitational wave background in the CMB through the polarization.
Yeah, the P mode of the polarization.
To the B mode. And that hasn't been seen.
Not the gravitational wave part. B modes have been measured, but those B modes are E modes converted by V cleansing. But there is a area in which that B modes can only be created by gravitation. That is yet.
And the anisotropy thing, nothing has been.
Nothing has been seen
The
except for
direction.
these intriguing things, but yes.
Yeah. But there was a lot of work earlier of that. But now that has
Yes,
stopped.
you have actually, so we don't talk about it much, but Planck had a subgroup which explored all possible topologies that can be put down to the Planck data. They were all rotating young models and all kinds of things. So this is part of our job, right? We have the best data, we need to put the best limits on everything.
So, yeah.
Yeah, so it's just a sort of layman's question. Of course, your talk was popular, so you want to motivate people. But I mean, you didn't talk about the real crisis in cosmology regarding, say, measurement of the H naught, etc. So how do you regard that part? I mean, H naught tension, sigma naught tension, etc.
Sigma naught and H. Okay, again, you're talking to the wrong person.
No, but so of course, being a CME person, you will not trust. Maybe is that your attitude? That
Yeah,
supernova
so I will
measurements
tell
are
you to
not.
show this plot and limit that. Okay, so these are the measurements over the years from everything else. Okay, with local. These are the measurements from CME.
Yes.
Right. So yes, double map and Planck have a no. Not really
Coming.
height there, but there is some hope that, I mean, not hope, it's believed that soon, even in our next run, I hope, we will start seeing enough neutron stars, and in the whole fight, like by 2030s, we will have enough neutron star events that we can pin down Hubble constant, at least to the accuracy where this big gap that is showing up between the local measurements and CMB can be discriminated. Yeah, the current question here peaks around the CMB one, but can be. Thank you. So,
Any more question?
One more.
Yeah.
Which observations are completely model independent?
which one?
Which observations, conclusions are completely model independent?
Which ones? So I can tell you the one where I showed you the ring of in the polarization. So that one is as model independent as you can think of. I showed you a much better actual measurement here. This is, I mean, very difficult to imagine something happening where the polarization field has a ring-like structure, exactly at the scale that you expect the cosmology. So this is model independent. The peaks lining up this model independent. Okay. And then the fact that there's gravitational instability at okay, so the other part. Yeah, this, which shows you the V cleansing effect, and you can ask, this is V cleansing effect. This is a hotspot of the cosmic infrared background that plant itself measures. Hotspot of cosmic infrared background is where stars form. That must be the most dense areas. If you stack all the weak lensing effects around places where there's a lot of matter, we know from infrared background, then there's a convergent field. This is about a 46 effect. These are absolutely robust things that the weak lensing is happening. These are very nice ways to see that these are. So these are really things that are textbookish. I mean, in the sense that if I teach GR now, I'll give this as the best example of measurement of weak lensing.
Yeah, but they are model independent, but they still do not go against the standard cosmological model.
No, yeah.
But they could be explained by some other models. There any chance of
Yeah,
that?
there is. I mean, this weak lensing field has this. If you have modified gravity theory, as you know, there's this. There are two scalar modes in fluctuations, and they are identical in our case. But in many models, they're different. And weak lensing is caused by one of them. And so, if that effect doesn't match up with the effect of the density, then it may have some. Yeah, this, as I said, all open. What we know.
Okay, thank you. Thank you. There is question, so that sure. Others to that please. Hand over this small debate to the speaker. Stop here, and I think we have. Thank you very much.